Hey, so before I start today's vlog, I just want to make a tribute. Now, as you may or may not have heard, but Neil Armstrong, the first man to step on the moon, has sadly passed away. So, for Neil Armstrong, we salute you, sir. So what I'm going to be doing for today's vlog is a revision guide for AS Electronics, both for my benefit, so I can help revise of last year, so I don't have to make sure that when I go back in September I haven't forgotten everything, and for the benefit of you lot who are just going to start your AS Electronics, as I'm obviously probably not going to go through the entire syllabus in one vlog. I'm probably going to continue based on other vlogs, depending whether or not I have something else to vlog about, and probably I'm going to do this after VEDA as well. I don't think I'm going to spend my next 6 vlogs purely doing this, unless I have nothing else to vlog about. But this will be the first in possibly many revision guides to electronics. So today will be a quick introduction to electrical theory, which strictly speaking you aren't tested on, but it's just basically the basics, the underlining most stuff you should already know from GCSE physics. Folder. So the first thing is basically structure, matter, specifically an atom. Now, I'm not going to bore you in the details because you don't really need to know them for AS Electronics, but basically protons have a positive charge, electrons have a negative charge, electrons are held in a cloud around the nucleus, held together by the attractive force of the protons. So from GCSE physics, you'll know that metals have a concept called free or conduction electrons, and this is apparent in some of materials as well, but especially metals. Basically what this means is that the outmost electrons of an atom are held together by very weak forces and can jump from atom to atom. Some of these forces are so weak that at room temperature, some electrons are in the process of randomly jumping from one atom to the other, so much that they're not actually associated with one specific atom. They're basically constantly moving around from one atom to the other, and that's essentially what a free electron rather is. Now, these electrons still repel each other because they're both negative, and this prevents moving electrons from bunching up. And so what you have here is evenly distributed electrons. And what an electrical power supply does is apply the force to these electrons, making them move in the same direction, therefore an overall movement of charge. So basically what electricity is the flow of charged particles, especially electrons. Now consider this basic diagram with a bulb, battery and wires connecting the two. Now before the circuit has been turned on, the utmost electrons of the atom are currently moving around randomly between the atoms, but their repulsive forces, by nature of them all being negative, keep them spread evenly throughout the wire. Now when you turn the circuit on, the electrons from one side of the power supply are moved to the other side, thus repelling the electrons on the other side, which then repel the other electrons, and then repel the other electrons in a sort of caterpillar effect, as it were. Therefore, moving the electrons around the circuit, you get a movement of electrons, a flow of charged particles, electricity. So that's basically what electricity is. Now, the units of electricity, how you're going to measure electricity. Now, you have standard prefixes in electricity, and you probably already know these from GCSE physics, but in case you don't, they are giga, mega, kilo, milli, micro, nano, and pico. Now, giga is
1.21 gigawatts. Great Scott! What the hell is a gigawatt?
Giga is with the symbol G and is 10 to the power of 9. Mega is symbol M, 10 to the power of 6. K is 10 to the power of 3. m with 10 to the minus 3. You go to micro, which is the Greek symbol mu, which is 10 to the minus 9. We have nano, which uses n, 10 to the minus 9. Sorry, micro is 10 to the minus 6. And pico is 10 to the minus 12. It's important to know both of these, x volts, x times 10 to the minus 9 volts, or you'll see 10 nanovolts. You'll need to change them between the two. It's also useful if you're doing physics to a level. So the first unit of electricity is current, represented by an I, and it has a unit of amperes, represented by an A. Current is the rate of flow of charge. Current basically being, if you chose one point of a circuit and counted how much charge passed that point in 1 second, that would be your current, and basically how much electricity is flowing. In case you didn't get that, it's like standing on the side of a motorway and counting how many cars pass you in an hour, because the cars being charged and an hour being a second. That's your current. And while we're on the subject of charge, charge is another unit of electricity with the symbol Q, and it's measured by the unit coulombs with the symbol C. 1 coulomb is basically the charge passing a point when a current of 1A flows for 1 second. And so basically, and here's your first formula of my fantastic revision session, a coulomb, Q, is I times T, current times time. Voltage, symbolized by a V measured in units of volts, which is also symbolized by a V. Now, electricity is forced around the circuit by a power supply, which would imply that power supply is providing an energy that is being used up to push electricity around. And voltage is a measure of the size of these energy charges. Now, voltage comes in two forms: electromotive force, which is a force provided by a supply to push electricity around the circuit, and potential difference, which is a force pushing electricity from one point to the other. Thus, 1 volt between 2 points represents 1 joule of energy for each coulomb of charge passing between these points. Now, voltage never flows, moves, or otherwise performs. You consider it just as a force that pushes energy, that pushes charge, and a measure of energy used when the charge moves. And now for your second formula. Now, if work done, represented by E, is the number of coulombs, represented by Q, times joules used per coulomb, in other words, volts, represented by V. And because Q is current times time, we get E equals V by T. And because power is work done divided by time taken, therefore P equals E divided by T, which means that P equals V I T over T, which basically means P equals V I. Power, watt in watts, is voltage times current. You tend not to need to know how a formula is derived, but you need to know basically how, for example, you get from Q to IT. So you need to know Q is the same as IT. So then if you ever get a question where you're just given, if you need to work out, for example, work done, and you're only given voltage, current, and time, you know that you can translate current and time into coulombs and then times that by voltage to get work done. And finally there's resistance, but as I've probably already taken a while with the others, I'll mention resistance in the next time I do one of these, as well as going through Ohm's law and whatever heck is in my formula after that. And hopefully I'll get better at actually making revision guides and actually some use. Till next time, bye.
Yes, it's very fine. Yeah, I'm going to step off the limb now. That's one small step for man, one giant leap